Hi, welcome back to the Math Studio. We're going to be taking a look at some conversions of polar form to rectangular form and back. You might be wondering, what is polar form? Well, polar coordinates are just a way of thinking about coordinates in space that is a different way than the Cartesian coordinate system. Cartesian coordinate system just defines points in terms of their distance from two axes, or three if you're talking about three dimensions. But you have the vertical y-axis and the horizontal x-axis, and the distance from each of those determines the point. In polar form, you're interested in where you are in terms of an angle and a distance from an origin. So I love this picture here of these tiles where you have three of the tiles represent the polar coordinate system, and then that top left tile has the regular Cartesian coordinate grid. That is a great way of picturing exactly how Cartesian coordinates and polar coordinates are related. There are relationships, there are things that are similar, but also this circular sort of picture of the polar form is a very, very different way of thinking about points. So in general, what we're going to be doing is in rectangular coordinates, uh, uh, you're going to be, let me pull up my iPad again. Sorry, I was not paying attention to where I was in the lesson. So in, and I don't even have my microphone there. In rectangular form, let me pull this up here. So rectangular, you have your axes, and then a point up here, you're going to measure these two distances. This distance is the x-coordinate, the horizontal distance, and the vertical distance is your y-coordinate, and we call that the point xy. In polar form, you have a similar situation. You have a point, and you're going to be measuring a distance, but here's how we're going to measure the distance. You're measuring the distance from the origin, and I'm going to call that r for the radius. And then you're also going to compute this angle, and so you have r theta. Now, our job in this lesson is to work on converting between rectangular and polar coordinates. It's not all that complicated. There is some fine print that we need to go over. Let's see if I can get the fine print. There it is. So anyway, first off, if you know r and theta and you want x and y, it's pretty straightforward. You just use your knowledge of Pythagorean, or rather your trigonometric knowledge of sine and cosine, and you get these formulas right here. X is r cosine theta and y is r sine theta. It's easy to see why that is if you just draw a triangle. In fact, let me do that right now so that make you happy. Here is my triangle, theta, and you can see that the x-coordinate is related to r, specifically cosine of theta is x over r, so x is r cosine theta, and then the y, that's sine of theta, is opposite, or y, over hypotenuse, which is r. And so that's why things look the way they do in this formula. Now, going the other direction, if you know x and y, and you want to compute r and theta, it's a little bit more complicated because of the fine print. Specifically, the r is pretty easy. You use the Pythagorean theorem, r squared is equal to x squared plus y squared, and so r is the square root of x squared plus y squared. But the angle is a little harder to get because there's this fine print. The tangent of the angle is y over x, but because theta, because of angles and tangents repeat themselves every 180 degrees, you won't necessarily know which quadrant you're in, and so you have to be careful. That's where the fine print comes in. When you're computing theta, make sure you end up in the correct quadrant. You'll see this happen in just a minute with the examples. So speaking of examples, I have several here to look at. So give me a sec. And so here are several examples, and I'm just going to roll through these pretty quickly. So we'll do the first batch. In fact, In fact, I just had to stretch things out a little bit so I had more room. So we're going to do these little one at a time here. So this is r, this is theta. In fact, let me make this a little bit bigger for you so that you can see better. So there's r and theta, and we're going to do x is r cosine theta, so 2 times cosine of pi, and y is 2 times sine of pi. So that's this one right here, um, which gives me the cosine of pi is -1, so this will be -2, and the sine of pi is 0. So that is that. Okay, I'll change colors so that we don't get confused, hopefully. Now we'll do this one down here. Um, so we have 1 times the cosine of pi over 3 and 1 times the sine of pi over 3, which is equal to, let's see, the cosine of pi over 3 is 1/2, and the sine of pi over 3 is radical 3 over 2. So this will be 1/2 and radical 3 over 2. All right, changing color again. This one, I will have the coordinates 1.5 times the cosine of pi over 4 and 1.5 times the sine of pi over 4. I think you get the picture here. This is cosine of pi over 4, and the sine of pi over 4 is radical 3 over 2. So this is a straightforward one here. It's going to be 1.5 radical 3 over 2 and 1.5 radical 3 over 2. We could clean that up a bit. Okay, this one, we'll skip this one because it's, and we'll skip this one as well. They're all pretty straightforward. But this one right here is a little bit different from the others. So I'm going to pull this down here and do this. This is going to be 1 times the cosine of 1 and 1 times the sine of 1. R times cosine theta, R times sine of theta. Now, this is cosine of 1 radian. Make sure your calculator is in radians, and you get 0.5403 for the x-coordinate, and then the sine of 1 radian is 0.8415, and that would be that one. Going the other direction, this is where we have to be careful and be conscious of that, the fine print. So the number 1, 2, we're first of all going to compute r. That's going to be 1 squared plus 2 squared, which is radical 5. Here, I'll do this. I should have spread these out more, I guess. And then tangent of theta is going to be y over x. But bear in mind, we want to make sure we end up in the correct quadrant. You see, your calculator will only give you, when I do inverse tangent of 2, this is going to give me an angle between negative pi over 2 and positive pi over 2, which in our case, in this case, is fine. This is radical 5 for r, and then 1.107 is the angle. So that's this one here. Let's skip this for now and go on to this one, because that illustrates this next one. That's going to illustrate this problem that we have with the angles. So with this one, r is equal to the square root of radical 3 squared plus 1 squared. I know it's negative radical 3, but when you square it, it becomes positive. So I'm going to ignore that. And then this becomes just 2. So r is 2. The tangent of theta is y over x. So -1 over negative radical 3, which is 1 over radical 3. So let's go ahead and punch that into the calculator. Inverse tangent, so theta is the inverse tangent of 1 over radical 3. And I got 0.5236. Now here's the problem. That point is the point negative radical 3, -1, which is right here. So negative radical 3 in the x-coordinate and -1 for the y-coordinate. But this angle is this angle right here. And so for us to get the correct angle, we have to add pi. So make sure you diagram these to make sure that you get the right answer. You're actually going to add pi to this. And when I do that, so generally that's what you end up having to do, but I wouldn't take that as the way that it's always going to work. This bigger angle here, when I go all the way around, is going to be 3.665 radians. So my final answer is R is 2, and the angle is 3.665 radians. All right, let's just do one more of these. Let's see, 4, -3. That one's kind of fun. No, that one's too easy. This one is kind of fun. We'll do that one. So we'll do that one, and then we'll pause the video and do one more video for this section. So first of all, R is the square root of 3 squared plus 4 squared, which is 5. And then tangent of theta is y over x, so -4/3. That means that theta, well, let's see what we get when we do the inverse tangent of -4/3. I do that on my calculator and I get -0.9273. That is clearly not the right angle because this point, when I graph it, I go -3 and up 4. That's this point. Whereas this angle is actually down here in this quadrant. So that angle is the wrong direction. So once again, I'm going to have to add pi to this to get the correct angle. So what I really want is I want to add pi to this. I'll do it on my calculator since I've still got this here. And so my actual angle is 2.2143. So my correct answer is R and theta. There we go. Oops, put coordinates around it. Okay, so we'll pause, and then in the last video, we'll just take a look at some regions and other conversions.